Welcome back to another BGCSE Past Paper Review. Today we're going to review a chemistry paper. We're going to review paper 3, and it was from the year 2020. Again, before you start this examination, write a school number, your candidate number, your surname, and your initials. Please read through the instructions carefully before you start this examination. Also note that you will get sometimes some additional information that you need for the examination. Again, they also provide you with a periodic table that you can make use of if you need to do so. Now let's jump into question number 1. And in question number 1, part A, it said that an experiment was conducted where solid zinc metal was added to copper 2 sulfate solution in a beaker. It said write a balanced chemical equation for the reaction, include state symbols. So let's get right into it. And we're going to have copper sulfate, which is CuSO4. Okay, I'm going to put the 4 on. All right, so that will react with zinc, and that is Zn. All right, and so you will get as a result, you get zinc sulfate. All right, again, I'll put the 4 on, plus copper, which is Cu. All right, and this equation is balanced as it is, but let me put on the missing number. So this will be 4 right here, SO4. And this is also SO4. All right, so now I'm going to put on the state symbols now. All right, so let's quickly do that. So the state symbols, let me put here in probably blue. Okay, great. So copper sulfate is aqueous, so I'll put on AQ right there. So it's going to be AQ. Okay, and you put that in bracket. Zinc is a solid, so you put S. That in bracket as well. Copper sulfate is aqueous, so let's put AQ right there. And copper is a solid, so you put S for that. All right, and that will be your balanced chemical equation between copper sulfate and zinc. All right, so now let's jump into the next part of the question. And this part of the question, it is part 2, so list 2 observations that show the reaction is complete. And so to make sure this reaction is complete, there are a number of changes. You will see 2 particular changes. Is that one, which is copper sulfate, that is a blue solution, will turn into colorless zinc sulfate. So therefore you see blue to colorless. So that's one color that you'll see a color change. The blue to colorless. Another possible observation that you will see right here is that since copper is formed, then you're going to see the copper deposit at the bottom of the solution. It will be a suspension of copper, and so you see copper metal. So what you'll see red to brownish deposits at the bottom of the test tube or the bottom of the beaker, whatever you have the substance reacting in. All right, so those are the 2 main observations that you'll see. Now for part 3, it's a state how the reactivity of zinc compares to copper, and is that zinc is more reactive than copper. So zinc is more reactive than copper. All right, so great. Now let's go to the next part of the question, which is part 4 of this question. It said bauxite is an ore of aluminum. Said bauxite contains Al2O3. Calculate the percentage by mass of aluminum in Al2O3. All right, so now what we're going to find here, we're going to find the total mass, which is the molecular mass of this compound. And so let's do it by elements. So first we're going to find aluminum right here. So Al, let's say Al equals to, and in this we have 2 atoms of aluminum, so therefore we're going to say Al, we're going to be 2 multiplied by the relative atomic mass, and that is 27, which will give us 54. And then we're going to do the same with oxygen. And so oxygen here is, how many molecules? There are 3 molecules. We're going to multiply that by 16. And so here you'll get 48. And so the total mass will be, out of both of them together, you'll get 102 grams. So that is the molar mass for aluminum oxide. Now what we're going to do next is to find the percentage now of aluminum. So let's say the percentage of Al. So that will equal to 54 divided by 102. And we'll get right here 52.94%. Okay, so that will be the percentage by mass, all right, of aluminum in aluminum oxide. All right, so for part 5, it said the method of extraction of a metal depends upon its position in the reactivity series. It said name the method by which aluminum is extracted from bauxite, and this is electrolysis. So this is electrolysis. All right, so great. Now, the next part of the question right here now, it said that name a metal other than aluminum that is extracted by a similar method from its ore. And this could be sodium and even calcium. So it could be sodium. All right, I'm going to put calcium as well, which is another option there. All right, so I'm just giving extra information right here. They only ask for 1. All right. So great. Let's move on to the next question now. And so for part 7, it says buildings can be made using aluminum because it is malleable. That means it could be in a different shape or different shapes. It's a state one other property of aluminum that makes it suitable for buildings. And one main good reason right here is because it can reflect light. It's shiny, so it reflects light. So it has a high reflectivity. All right, so it can reflect light easily. So I must make a point right there. Reflects light. And so once it can reflect light, then it will make the building a little bit cooler than using other dull metals that will absorb heat more. Another important property here, which I think is even most important than the one listed above, is that it is corrosion resistant. It has a good corrosion resistant property. Okay. All right. So it is corrosion resistant. And that is a very important property. I think it's even better to list than the one I list above, okay, in terms of reflecting light. But I mean, you want it to last on a building for a long period of time, so hence can resist corrosion is a very good property. Question number 2. It said this question is about metals found in the periodic table. Here it asks us now to complete the table. And so if you look in the table, you see elements, then formula of oxide, and type of oxide, and ions present. And so here we're going to say sodium, and the formula for sodium oxide is going to be Na2O. So it's going to be Na2O. Or let me just say NaO, and I put my 2 in. Okay, so Na2O. Okay, great. And then the other, the type of oxide right here is going to be basic. And the ions present in sodium oxide will be sodium ion and the oxygen ion. And so here going to be Na. Let me just put Na right there. It also will be O. But let me put on the charges. So this will be Na plus. And oxygen will be 2 minus. Okay. All right. So good. Now going on to the other metal, which is magnesium. So magnesium to form magnesium oxide will be All right, and those will be the metals present there. Notice a positive 2 and negative 2. That is why there's one magnesium and one oxygen. All right. Now, zinc oxide. All right. Again, zinc oxide is also basic in nature. All right. I'm going to tell you why they're all basic in nature. And the ions that are present in zinc oxide will be Zn and oxygen. We know that the charge on oxygen is 2 minus, right? And if the charge on oxygen is 2 minus, then the charge on zinc has to be 2 minus as well. Why? Will have to be 2 plus, sorry, but it has to be value of 2. Why value of 2? Because 2 minus and 2 positive will cancel out each other to give you 1 atom of each of the element, okay? So it will be the same value of charge, but opposite charges. All right, so basic oxide, the reason why they're basic oxide is because they will react with water to form hydroxide. So you can make a note of that these oxides, they will react with water to produce hydroxide. Okay. So for example, you may have zinc hydroxide, magnesium hydroxide, sodium hydroxide if they react with water. All right, so for part B, it says zinc is an important transition elements. It's a give 2 properties of transition elements that are different from group 1 elements. All right, so in other words, besides they being metals and so on, what is so different about these transition metals? And so I'm going to give you some answers right here. So transition metals, one important property about them is that they exhibit more than one oxidation state. Okay, so they have or exhibit have more than one oxidation state. Group 1 elements will only have a positive 1. All right. Another property right here that we can list is that they're generally colored ions, so they form colored ions in water. So like here, you notice you see copper is colorful. All right, so they normally generally again form colored ions in water generally. Okay, so they form colored colored ions in water. And next property right here, they have a number of different properties that make them different. Is also they have a high melting point compared to group 1, so they have higher melting point. Okay. All right, so higher melting points. They also have higher density as well. So the higher density compared to group 1, higher densities. All right. They also have greater strength, so they are stronger. All right, so they are stronger. All right, and they're harder as well. So they're harder or stronger. I could make a note of that. So they're harder and stronger. Okay, so these are generally properties of the transitional metals compared to the group 1 metals. All right, so let's continue to part 2 of part B. It's a solution of zinc ions produces a precipitate with aqueous sodium hydroxide. State the color of the precipitate, and once zinc react with sodium hydroxide, the precipitate here is going to be a white precipitate. So this will be white. All right, so great. Now jumping on to the next part of the question, and for part 3 of section B, it's a chromium has 4 isotopes. Its composition is given in the table. So you have the isotope with mass, and you can see the mass, and then you see the relative abundance, which is the percentage that they exist in. And right, they say calculate the average atomic mass of chromium. Round your answer to 3 decimal places. So what I'm going to do is quickly, all I need to do is to multiply the mass by the percentage of each. And so what you could do is divide the percentage by 100 and go straight ahead and start to multiply. So I'm going to skip that step of the multiplication of the division by 100 and just go straight into it. and just multiply by the percentage as a decimal. So what I'm going to do right here, I'm going to say 51.94, okay, multiply by the 83.79%. So I'm going to just go straight ahead and say multiply by 0. So I already divide that number by 100, so you could just divide it. So 0.837. All right, and that will give us there 43.520. And so the next value right here, which will be 52, so going to be 52.94. Okay, multiply that by the percentage, which is 9.50%. So that's going to be multiplied by 0.095. Okay, and that will give us a value of 5.029. All right, so let's go to the other one, which is 49.95. So it's going to be 49.95 multiplied by 4.35%. So it's going to be 0.0435. And that will give us here 2.173. All right, and then the last one right here is 53.94. So going to be 53.94. And we're going to multiply that by the 2.36%. So going to be multiplied by 0.0236. And that will give us a value of 1.273. Okay, and what we're going to do now is add up all these values. So we're going to take the sum of these values, and that will give us our total. So let me put it right here. Okay, so let's put it right here as a total. So the total here, I'm also going to change the color as well. The total right here will be 51.995 grams. So if you have run off this number, you get 52. So if you look in the periodic table, you will see 52 grams, right? So I must make it right here. So in the periodic table, based on the periodic table, I'm going to put it right here, based on the periodic table. So in the periodic table, you will see here 52 grams, okay? All right, so by calculation, however, based on the abundance of isotopes, is 51.995 grams. All right, so great. Now let's go to the next part of the question right here. So describe the bonding in zinc. And zinc, to have zinc is a metallic bond. So it's a metallic bond. So I'm going to say metallic bond first. All right. So form a metallic bond. And what is happening here is that there, in a metallic bond, you have a sea of electrons. So there is a sea, let me quote unquote that. So there is a sea of electrons. All right, so let's put that in open and close quotation. All right, that, and the sea of electrons, what will happen here, right? They will move freely. So there's a sea of electrons that move freely, okay, that move freely, and they're moving freely throughout the entire metal, right? To move freely throughout. All right, throughout the metal. All right, and in that metal you have cations. Okay, in the metal where cations, all right, are held closely together. All right, so all I'm doing right here is to describe what ionic bond is. Right? So in this is a metallic bond. So this is in the metallic bond, you have a sea of free electrons just moving about, and you have positive ions, which are called cations, that are close together. Okay. All right. So in, for example, copper, just a pure copper. All right, gold. All right, they are metallic bond. All right, so let's jump on to the next question, which is question number 3. I'm trying to go as fast as possible. All right, and in question number 3 here, it said that a 0.0115 grams sample of sodium is added to water in a large beaker. The temperature of water increased. So the table shows the result. So again, the temperature of the water increased. And right here it asks us now, it's a completed table by calculating the temperature change. And so the temperature change will be 25 from 48, which gives us 23. So 23 will be our answer right there. For part 2, actually, it said the highest, the heat given out during the reaction is calculated using this equation. So the heat given out is used by this equation, which is say M times 4.2 times change of temperature, and 4.2 is the specific heat capacity of water. So what we're going to do right here now is to put our mass right here, and our mass in the question was given as 0.0115. So let's put that here. And so let's do that quick. Let's a little bit up. All right, great. So I'm going to multiply my mass. So M represent mass. So it's going to be 0.0115. We're going to multiply that by the 4.2 given there, which is the specific heat capacity of water. Multiply by the change of temperature, and the change of temperature in our chart here is 23. So we're going to multiply that by 23, and that will give us here 1.1109, and it's going to be in joules. Okay, so our answer here is, I'm putting all the numbers there, 1.1109. And you can run up to 3 decimal places or 2 decimal places based on the preference, or if the exam actually asks you to do that. So for part 3, it's determining the heat given out when 1 mole of sodium reacts with water. So what I want to find here is heat given out when it reacts with 1 mole of sodium. All right, so 1 mole of sodium reacts with water. So first and foremost, what you need to think about, right, is how we're going to find the number of moles. So first and foremost, you're looking here at sodium, right? So now remember, the mass number for sodium is 23, right? That's the atomic mass number for sodium is 23. But to find moles, the first thing we have to do is to divide the mass, okay? Divide the mass by the relative mass, relative molecular mass, or relative atomic mass. And the mass given here was 0.0115. So let's put that there to find our moles. All right, and so therefore what we're going to do, and remember what I want to point out right here, this is saying joules per moles. So what I want to understand by even this formula, because this unit, I should say, give you the formula, joules per mole. So you're going to divide the joules, which is right here, by the mole. So first you have to find the mole. All right, so mole now is given as I said, going to be our mass divided by the relative atomic mass in this case. So going to be, so mole will equal to the mass given, which is 0.0115, right? We're going to divide it by the 23, which is the atomic mass of sodium, and that will give us here 0.00, that's 3 zeros, 5. So that will be the mole of sodium. And then now, since you have the mole, you can divide the energy that we calculated right here. So we're going to be energy in joule. So notice here, joule per mole. So here we need to divide now the energy, which is 1.110909 over the mole that we just calculated, which is 0.305, and that will equate to our joule per mole, and that is 1.8. Okay, so it's going to be 2,221.8. So 2,221.8 joules per mole. So that will be our answer right there. All right. So now we can jump on to the next part of the question. It said the equation for the reaction is sodium plus water to give you sodium hydroxide and hydrogen. So here it said draw an energy level diagram for the reaction, label the reactants and products, and this is, I think this is a 2-mark question. All right, so what we're going to do is to draw our graph, or outline our graph real quick. But there are a number of things I want to point out here real quickly. All right, so let me just, put this in blue. This should be all right. All right, so I'm going to put a line right here, which is my y-axis, and I'll put my x-axis right here. Now, there are a number of things that you need to point out or need to be clear. This reaction here, it is an exothermic reaction, okay? So the reaction is exothermic. All right, when sodium react with water to produce sodium hydroxide, heat is given off. So it is an exothermic reaction. Okay, so I could put it right here. So this reaction is exothermic. All right, so now we have that. All right, so what I'm going to do now is to get into the graph. And so once it's an exothermic reaction, what you need to have is 2 things. And they mention about the reactants and products. I'll put the reactants somewhere up here, because the reactants will be higher than the product. Because remember, the energy is lost to the environment for exothermic reaction. So the final temperature in the product will be less than what you started out with. Again, what I also want to show you, since I have the points for reactants and product, I want to show you the intermediates. And so the graph will be connected like that. All right. All right, so now let's jump into a few things that we must have here. So the reactants versus product. So here would be the reactant. All right, so here let's just put R. Please remember that R is reactant. I'm just trying to do this as fast as possible. And P will be the product, okay? So the reactants will be here and the products will be on this line. Now, what will be the reactants? There are 2 reactants here, the sodium and water. So Na is one of the reactants, okay? And water, which is H2O, is another reactant. Okay, so H2O, we have those 2. And then as a product, what we have as a product is sodium hydroxide. So I'm going to say sodium Na OH. Okay. All right, so that will be one of our products. And also what you form as well is hydrogen gas. So it's going to be H2. All right, so great. However, though, before the reaction takes place, you'll form some ions. So there are 3 ions that will form here. You'll form sodium ion, which is Na+, is in group 1. You'll also form the hydrogen ion, and say coming from water, you may have the hydrogen ion right here, okay? And you may also have the hydroxide ion as well. So hydrogen is a positive ion. And you also form the hydroxide ion, which is OH, okay? And that will be a minus, okay? And so hydroxide ion will react with the sodium to form sodium hydroxide, and the hydrogen ion will form the hydrogen gas. All right, so a point to note, again, key point to note, once you're doing this type of reaction here, there are a number of things, again, I need to point out. Again, I want to do this real fast. I could finish with this. All right, so what I want to point out here is that I'll make a line across here, all right, this green line right here. And then let me make a broken line coming across here with this green line as well, going straight across the graph. All right, now the distance between these 2 green lines, all right, will be our energy that is being released. So from here to here, from the products, all the way to the reactant, that will be the energy release. So this is energy released. All right, I'll label that. And then on top here, all right, let me put it a little bit over so you don't get confused with these arrows. So from the reactant to the intermediate or the free radicals, all right, this is what they call the activation energy. I'm going to label all those for you right now. So this will be the activation energy. All right. I represent the activation energy. And this point here, which is the line from the product up to the reactant, that is the energy that is being released. If it was an endothermic reaction, then it would be the energy that is being absorbed. All right, so great. Now, I just want to point out a little thing to you right now. Maybe it will help you. I'm not sure if you may even use it. But what I want to point out is that the amount of energy that was released right here is 1.1109, right? And if that's the amount of energy that is released, I just want to point out something here. So let's say I put a value of 1 joule right here, right? Then we can estimate the amount of energy that will be right here, because remember that the energy release must be 1.1109. So here we could estimate this to be like 2.11, right? 2.1109. Okay, because remember the difference between the 2 points here must equal to 1.1109. Okay, let me say 09 joule. Okay, 09 joule. All right, so great. So that's a way to estimate how your graph will look in terms of the energy. Again, this is only 2 marks. You're looking for the reactants and the products. All right, and you can show your energy as well. But I just want to show you some extra stuff. All right, anyway, let's jump on to the next part of the question. All right, and I hope you understand this part where I said that 1 joule, this could be any number, matter of fact, but the difference between this number and this number must give you 1.1109 joule, because that's what the energy that was released by calculation. All right, so now let's jump to the next part of the question. And this part of the question is a diagram shows equipment used in the electrolysis of brine, and brine is sodium chloride solution, so it is table salt solution. And so this is an electrolysis circuit or electrolytic circuit. And so the electrodes used are inert. And it said, why are inert electrodes used? And it is used for one simple purpose, and it's to prevent, I'm going to quickly do this. Yes, to prevent the electrodes from reacting with the ions, all right, or with the discharge ions, okay? Okay, to prevent reaction with the discharged ions, okay? All right, so the electrodes, they will not react with the discharged ions at all, all right? So if you need to collect the ions that are discharged or the gases, you could collect them, all right, instead of them reacting with the electrodes. And again, if they react with the electrodes may even get heavier. Also, the conductivity, depending on what is being discharged, can also decrease of the electrodes as well, because they become corroded or they may even erode. All right, so let's jump in this. It said, write the half equation for the reaction at the negative electrode and also at the positive electrode. But before I go into writing the half equation, let me just jump into something real quick and talk about what is happening in the electrolytic circuit. And so in the circuit, we are using brine solution, right? So if you're using brine, which is a salt solution, sodium chloride solution, the point I want to make right here is that if the electrolyte is a solution, then you'd have 4 ions present. Or in other words, if the electrolyte is aqueous, then you have 4 ions present. The 4 ions that are present, you'll have sodium ion. I'm just going to do this. I'll put on the charges when I'm finished. You also have hydrogen ion, which is coming from part of the water, okay? And you will also, let's put this a little bit further. I hope we could hold right here, a little bit too close to that. All right, great. All right, and hydrogen. All right, and then you also will have chlorine as well, okay? All right, so chlorine, and you will also have the hydroxide ion from water. So the OH and H, they come from water. The Na and Cl, they come from sodium chloride. That's a solution. If this was molten, then you only have 2 ions, okay? Which would just be the sodium and chlorine. So if you have molten sodium chloride, it just be Na and Cl. But again, let me quickly put on the charges, because those will be important. So sodium is a +1, chlorine is a -1, hydrogen is a +1, and hydroxide ion is a -1. So what I just put the positive ions on this side to make it a little bit easier when I'm going through what I'm going to explain. And so this will be the positive electrode. So this is called the anode, okay? All right, and ions will attract to the anodes, And so here you have a cathode, and the cathode is the negative electrode, and cations will be attracted to the cathode. All right. So now we have that labeled. And again, the liquid in this circuit is called electrolyte. So we call that liquid electrolyte. Okay. Electrolyte. All right. Awesome. Now, point to note is because of the deposit of these gases or ions, you'll have gases being given off at both electrode. So on this side, because of the hydroxide ion that will be deposited here, what will happen here is that oxygen gas will be given off. So you see some bubbles. So you're going to have some oxygen gas coming from the hydroxide there. Okay. And so you're going to have O2 gas. And on this side, you'll have some hydrogen gas being given off on this side. Okay, so let's put our symbols, our amount of molecules. So it will be H2, and this will be O2. Okay. Also, what I want to point out with this circuit as well, right, is that inside is very important. Inside of the cathode, you have the electrons that are there. So these are just some electrons there. So electrons will be inside of the cathode, okay? And the reason for this is because the way electric current is being flown, right? And so the positive terminal will lose electrons to the negative terminal, and so there will be a surplus of electrons in the cathode. Now, why this is important? Because when the positive ions go towards the negative electrode, they will gain electrons and become stable. The same way, or the negative ions will go towards the positive electrode, and they will give up electrons. Because remember, the reason why chlorine and hydroxide are negative, because they have excess electrons compared to protons, right? And sodium and hydrogen, they are positive because they have less electrons compared to protons. Okay, so they go in here to receive electrons to become neutral, and these will go in towards the positive side to give up the excess electrons, and they will become neutral. All right, so just note that what is happening there. All right, and that will help us now in terms of our half equation, right? So our half equation at the negative electrode. So what will go to the negative electrode here, just to make a note right here, there are two ions, but the hydrogen will be preferentially discharged, okay, and will go towards the negative electrode. Likewise, hydroxide ion will go preferentially over chlorine and discharge its electrons. All right, so hydrogen will gain electrons, and the hydroxide ion will go and deposit electrons, and that's why you give off also oxygen gas. All right, so just make a quick note right here now. So here I'm going to show you this thing actually worked. And so at the negative electrode, remember the positive hydrogen will go there. So I'm going to put hydrogen to ion first. It will be positive, but I will so remember now, when the positive ion goes towards the negative electrode, it will gain electrons. I'm going to add electrons right here. Let's put E for now. I'm going to put E minus there. And then as a result, it will produce a more stable or molecule. So let's put H2. All right, and so let's put on the symbols real quick. So now it will be H plus here. So let's put the plus sign right here. Okay. And H2, which will be the molecule or the gaseous form, and E negative, which is minus. Again, we have to balance this equation. So the balance equation, since we have two H's here, we put two H's here, right? The two H's now make it become two positive. So you have to have two negative as well to neutralize, all right, out the two positives. So that will be now our balance equation at the negative electrode. And again, you can note the states of these. The hydrogen ions will be in aqueous form. So this could be AQ, okay? That's because it's coming from an aqueous solution. So it'll be aqueous. All right, so let's say AQ right there. And this will be a gas. Hydrogen gas will be given off, right? So let's call it gas. All right, just put the states there if you should need them. All right, so again, this is AQ. All right, just ignore my bad penmanship or my means of navigating this pen, but you get the drift. Now, the positive electrode. Now, what is happening at the positive electrode? Again, what will be preferentially discharged there is the hydroxide ion. And so what we're going to have right here is the OH. Okay, so it's going to be hydroxide ion. Now, again, it's negative. I'll put the negative on shortly. And so it will produce here, it will, remember now, it will give away electrons, right? So electrons will become a part of the product, giving away the electrons. The negative ions give away their excess electrons to become neutral. So giving away electrons. And so right here, it will form two things. Form water. So I'm going to say H. Let me leave a space right there for my two. So form H2O plus the oxygen. And the oxygen is what will be given off at the electrode that I drawn above. All right, so it give you oxygen gas. Again, let's leave a little space there because it's going to be O2 plus electrons. All right, and so let's put these in real quick. So again, this is going to be H2O. This is going to be OH minus. And again, oxygen gas is going to be 2 and our negative electrons. Now, what I want you to notice here is the equation is not balanced at all, right? So a way to balance this equation, here we have 2 oxygen and we only have 1 here, right? Easy way to do this, let the oxygen become even number. And so if I put a 2 right here, then you have 4 hydrogen and 2 oxygen plus 2 oxygen is 4 oxygen. So we can always put a 4 right here and make everything become the same. All right. And then what I could do is, again, if I have 4 negative electrons or 4 negative charge right here, it must lose all these 4 negative charge because 4 minus is saying 4 multiplied by this negative 1. So therefore 4 negative charges. So it must give away all these 4 negative charges. So I put a 4 right here to balance the equation as well. All right. So here we have a balanced half equation on either side of the positive electrode and also the negative electrode. All right, so take your time, go through it and make sure you understand it. Again, you could put your state symbols right here. Hydroxide coming from the solution, so it is aqueous. Water is a liquid and oxygen is a gas. So you could put on those state symbols. All right, this for part 3 is a state why sodium is not deposited during the electrolysis of sodium chloride. Why is not deposit? Now remember, sodium is a positive ion, right? Hydrogen is also a positive ion. So the thing is now is that the reason why hydrogen is being discharged over sodium is simply because hydrogen is more. So hydrogen is more reactive. Okay, so it's more reactive. And another way to say it is more reactive, you can say it is less stable. So it's more reactive or less stable. Okay, so therefore it will take the electrons faster than the sodium. Okay, all right. So the last part of this question is that during electrolysis, the sodium chloride solution turns into another solution. Name this solution. And this solution will be sodium hydroxide, because if you go back to it, you realize that the hydroxide ions that are there. Okay, so you get here is sodium hydroxide. Okay, so this will be sodium hydroxide. All right, so that's in this part of this question. Let's go on to the next part of the question. And this is part 4, which is the last part of this section A. Then we go on to section B. All right, so let's do this as quickly as we possibly can. It said hydrogen chloride is a gas at room temperature. Okay, so hydrogen chloride is HCl, so you can make a note of that. This is HCl, just in case we need it. Okay, HCl. All right, so it said draw a dot and cross diagram for 1 molecule of hydrogen chloride showing the outer shell electrons only. Okay, so there are 2 ways you could draw this, one with the shell or one without the shell. So all you need to do, remember that chlorine can only take on 1 electron. Hydrogen only has 1 electron to give or to share as well. So they're going to bond covalently. And so here you're going to have, I'm going to do it by circle first, then I will do it by line. So I'm going to have an H right here. Again, chlorine can only take on 1. Okay, so this would be Cl. Chlorine can only take on 1. Let's use the dots for chlorine. And let's use X for hydrogen. So hydrogen as one valence electron. Give up that one electron right here in the bonding section. And so chlorine will have 7 valence electrons. So you give away 1, remaining 6. You're going to put your 6 dots remaining there, occur in pairs. All right, so electrons travel in pairs. All right, and so there we have it. All right, another way to do this, you could just quickly say draw a H, okay, and Cl. All right, and here you could have your 1 electron given up from a chlorine, 1 electron given up from the hydrogen as an X, and then you have your 6 remaining electrons around your chlorine. Okay, so that's another way to represent this structure as well. All right, so great. Now let's jump on to now the next question. All right, before I move on, right, just in case you may need this in the future, right, or in the exam, if they ask for the structural formula, you just say H and a single bond, because 2 electrons form a single bond, so it'll be HCl. Okay, so hydrogen bond to chlorine with a single bond. All right, this is not a part of the answer, but just in case you need it. All right, so let's go to the next part of the question now right here. It said for part 2, it said hydrogen chloride is soluble in water. The solution produced turns universal indicator from green to red. All right, so moving from green to red, so moving from a neutral point towards an acidic point is to explain why the universal indicator changes color in a solution of hydrogen chloride in water. So again, what is important right here, as I mentioned, is that moving from green to red, green is pretty much the neutral point, and moving from a neutral point to a red, which is going to be acidic, is simply mean that the solution is acidic, right? So a point to note right here, the solution is acidic. And if the solution is acidic, that means it will discharge hydrogen ions, right? The solution is acidic and discharge hydrogen ion. All acidic solutions, they discharge hydrogen ions. And again, the degree of which they discharge hydrogen ions will determine the pH level. The faster rate, or the more or the stronger the concentration of hydrogen ions within a solution, the more acidic it is. Now for part B, right there it said that the solution was made up of 1,000 centimeters cube. All right, so the entire solution is 1,000 centimeters cube. Let's just highlight that real quick. The entire thing is this volume, 1,000 centimeters cube. It's a 35 centimeters cube of the solution neutralized 42 centimeters cube of a 1.21 mole per dm cube of hydrochloric acid. So this is the concentration, molar concentration, a matter of fact, of hydrochloric acid. Okay. Now it said write a balanced chemical equation for the neutralization reaction. And so the neutralization reaction here between potassium hydroxide and water. All right, so here say that so potassium hydroxide, all right, and hydrochloric acid. So this is hydrochloric acid right here, right? So both of them. All right, so I'm gonna put them right here. So we're gonna have our potassium hydroxide. So potassium hydroxide, okay, and that will react with the hydrochloric acid. So it's reacting with hydrochloric acid, and the hydrochloric acid is a 1.21 molar concentration. So here it will be HCl, which is hydrochloric acid, and that will give us now potassium chloride. So it's going to be KCl, and that will also give us water, because remember that an acid plus an hydroxide will give us salt and water. So the salt here is potassium chloride, and water, which is H2. Let's put our 2 right here. Okay, great. And so it asks us to balance this equation. This equation is balanced as it is. Okay, 2 H's on either side. Yes, so it is balanced as it is. All right, so we can move on from that and go to something else now, which is the next part of the question. It said calculate the number of moles of HCl in 42 centimeters cube of hydrochloric acid. So we're going to calculate now the number of moles. So in this now, first I want to look at, right? This is saying moles per dm cube, right? So if the concentration is mole per dm cube, it means that the mole was divided by volume. That's how you get the concentration here. So to get back the mole, what you have to do now is to multiply the concentration by the volume. And so let's do this. All right, so now the first thing here that I want to point out though before I start doing any calculation is that this is in dm cube, right? So this is per dm cube, this is centimeters cube. So what you want to do before you start that calculation is to convert your volume of the hydrochloric acid right here into dm cube as well. Because remember, you can multiply dm cube with centimeters cube, right? So what you can do is to make this becomes dm cube by dividing by 1,000. So you can just divide by 1,000. So I'll make a note right here that this is also 0.042. Okay, so that is the amount of dm cube that is there. Let's say dm cube right here. Okay, all right. So that's dm cube. All right, let me just put it back. I wonder if I no. Okay, that's dm cube. Okay, just make a note of that. That's dm cube right there. So right here now, I'm going to multiply my concentration by my volume in dm cube. So I'm going to say 0.0. Let's start with the concentration first. So I'm going to say 1.21 multiplied by 0.042, and that will give us now our mole, which is going to be 0.05082. I'm using all numbers now for a reason. So that will be your mole for right here. That's a one mark question. In part 3 is a determine the number of moles of potassium hydroxide in 35 centimeters cube of potassium hydroxide solution. Now, how do you go about do this now? We have to think about the chemical reaction. So the reaction will help us with this. If we have produced here 0.05082 moles of hydrochloric acid, that's the amount of hydrochloric acid used right here. But now we want to find now the number of moles of potassium hydroxide. Now you have to use the molar ratio of the equation now. And so the ratio in terms of quantity is a 1-to-1 ratio. And so since a 1-to-1 ratio in terms of one atom of potassium hydroxide react with 1 mole or 1 molecule of hydrochloric acid, then it therefore means then they are the same mole, right? So point to note right here, again, this is a 1 mark question again. So you're going to use the same mole, and it's simply because the ratio is a 1-to-1 ratio, okay? So because the reactivity ratio or the molar ratio in the reaction, okay? So because the ratio, let me just put that quickly for you, because the ratio is 1-to-1, then the mole of potassium hydroxide is also the same thing as the mole of hydrochloric acid, okay? So the mole here will be 0.05082, okay? So it's the same mole that we get on top is the same mole here, simply because based on the reaction, the balanced chemical reaction, 1 molecule of potassium hydroxide reacts with 1 molecule of hydrochloric acid. And that's why it is the same mole. All right, let's go down to the next part of the question right here. It's a calculate the concentration of potassium hydroxide solution in mole dm cube. Now, this is very specific in mole dm cube. Now, first and foremost, let's start this. Let's begin. Let's think about what concentration is equal to. Remember that concentration, I just want to kind of remind you about this, right? Concentration is equal to the mole divided by the volume, okay? Divided by the volume. All right, so here now, we already have our mole that we calculate up top, but we need to know the volume of potassium hydroxide. All right, so let's go for a volume of potassium hydroxide, where exactly it is. All right, so let's go up top here. I think it's there. All right, so great. Now we have in this, we have potassium hydroxide being 35, right? So 35 centimeters cube of potassium hydroxide solution was used. See it right here again. All right, so it is 35 centimeters cube. All right, that was used. All right, so great. So the amount of sodium hydroxide used was 35 centimeters cube. All right, so let's find the concentration of that now. So the concentration here is going to be the mole, which was 0.05082 divided by the volume, and the volume must be in dm cube. But just to make a note right here before I go to that calculation, remember that the volume here was 35 centimeters cube. So you're going to convert this into dm cube. All right, so divide by 1,000. So it's going to be 0.035 dm cube, okay? Just to make a note of that. All right, so once this is in dm cube, we can plug that into our thing now, because remember, we cannot use centimeters cube by virtue that they say they must be in moles per dm cube, not moles per centimeters cube. So here we're going to divide by the volume, which is 0.035. All right, and so our answer here in moles per dm cube, when we divide those two numbers, is going to be 1.452 moles per dm cube. All right, so great. Now let's go to the next part of the question now. It said calculate the mass of potassium hydroxide solid that was dissolved in 1,000 centimeters cube of the solution. Now this is where first thing you have to do something here. Again, what you need to do is to convert that volume into dm cube. And so 1,000 centimeters cube is 1 dm cube. So that is 1 dm cube. So that is fine. All right. So what we're going to do now, we're going to find the mole now in 1 dm cube. Okay, we're going to find the mole in 1 dm cube. So again, we already have our concentration, which is 1.452. Okay, so this is the concentration of potassium hydroxide. Let's go back to it and you'll see. Okay, so the concentration of potassium hydroxide is 1.452 moles per dm cube. Now we need to find the volume, which is 1,000. And 1,000, again, remember what 1,000 is, all right? And we want to find the mass over here first. First, I will find mole. Then we multiply the mole by the relative molecular mass of the compound. All right, so first, let's start this. So again, we're going to find mole first. So therefore, we're going to multiply the concentration here, which is 1.452, multiplied by the volume. Again, the volume is 1 dm cube, because 1,000 centimeters cube is same thing as 1 dm cube. Okay, let me just make a note of that. Okay, so the same thing as 1 dm cube. All right, now we established that. Now we need to now do a calculation. So when it's just say this multiplied by 1, we don't even need to do that because you know what the value is. So it's going to be 1.452, and that is the mole. Now, since we have the mole now, we need to multiply the mole by the relative molecular mass, or the molar mass, to get our mass. Because remember, mass of a substance is equal to the mole multiplied by the molar mass. All right, and so let's think about the molar mass of potassium hydroxide. So let's quickly calculate that. And so the molar mass of potassium hydroxide here will be our, so potassium is K, so that will be 39 plus oxygen, which is 16 plus 1. So all of that, let us put it right here real quick. So we're going to find the RMM. All right, so RMM, or the molar mass. So it will equal to 39 for potassium. Potassium is 39 plus 16, which is for oxygen, plus 1, which is for hydrogen. Okay. And the total of that is equivalent to 56. All of this is 56 right here. Yep, 56. So 56 grams, that's a relative molecular mass, or the molar mass. And so what we're going to do now is to multiply 1.452 by 56. Going to multiply this. Let me just put multiply right here. All right, matter of fact, let me just do it differently. And now it's in a different color as well. So right now I'm going to multiply my 1.452 by 56. And that will give us here now 81, a whopping 81.312 grams. All right, so that is the mass of potassium hydroxide that was dissolved in the 1,000 centimeters cube, or 1 dm cube. All right, next part of the question. Last part of this question, we jump on the part, section B. I know that's the part that they can't wait for. That is a long road, but anyway, let's see if we could go to it. Now, here's a suggest a piece of apparatus the students could use to accurately measure 42 centimeters cube of hydrochloric acid. And of course, the students could use, like example, 3 different types of equipment here. So a nice one they could use is a burette. They could use a pipette and also measuring cylinder. So I'm going to say burette. So burette could be used. All right, so burette could be used here. All right, and also, and also a measuring cylinder. Let's put measuring cylinder over here, right? So measuring cylinder. All right, so great. So any of those could be used. All right, but to make it really accurate, a burette will be very cool to use, a very nice one to use to get accurate results. What I'm going to do is to just scan through section B. Again, for section B, you need to answer only 2 questions out of 3. Answer all 3 for you. So I'm going to go through it, but I want to stop at this page because I'm going to come back to this page. I have all letters typed out, and so I'm going to jump to those, and then I come back to question number 7 for a reason using this chart. All right, so I will definitely come back here to finish up question number 7, part B especially. All right, so walk with me now over to section B. All right, so now we're in section B, right? And what section B is about, again, answer 2 questions out of 3. But again, I'm going to answer all 3 questions for you. So the first question is question number 5. It says students added 0.035 moles of magnesium ribbon to 25 centimeters cube of a dilute sulfuric acid. The magnesium metal added was in excess. The volume of hydrogen gas produced during this experiment was recorded every minute. Gas produced at room temperature and pressure. That's a very important point right there. It said the results of the experiment are given in the table. So we have the time in minutes. That's also important to note. Time in minutes and the volume of hydrogen gas. And this is per centimeters cube. All right, so first thing here now is said on plot the results on a graph paper and draw a smooth curve, and that's for 4 marks. And so here I have gone ahead to save some time, and I plot my graph, but I'm going to outline some things what you need to have in a graph. So again, just in case you might need this type of so again, let me just zoom into it a little bit and show you exactly what you need to have here. You need to have your axis labeled first and foremost, right? And properly scaled. So I label both of them, properly scale both axes, and then I plot my graph, and then I get my smooth curve as best as possible. Some of you will be better than me in drawing these curves. But yeah, that's the idea there. And again, match up your coordinates properly. Use a fine pencil as best as possible to get these nice curves. All right, so here now is a use your graph to determine the volume of hydrogen gas produced at 90 seconds. And so if I go back to my graph right here, right? So at 90 seconds is 1.5 minutes, yeah? Because on your x-axis is minute. So if you go 1.5 minutes, which is right here, it will take you up right across, which is be 17 centimeters cube. Okay, so that would be 17 centimeters cube. All right, great. It said the equation for the reaction is shown, which is magnesium plus sulfuric acid, give you magnesium sulfate and hydrogen gas. It's a state why the magnesium metal was added in excess, and simply because you want to make sure that the neutralization is complete. So you want to ensure complete neutralization of the acid. All right. So you want to make sure all the metals could neutralize. As a matter of fact, the metal could neutralize all the acid. All right, that's the most important thing right there. All right, so part 2 is use the equation to calculate the accurate mass of magnesium required to produce the final volume of hydrogen gas in the reaction at room temperature. Now, let me explain something to you real quick right here. Again, we have the volume as 48 centimeters cube, right? That is the volume of hydrogen gas as 48 centimeters cube. And how we get 48 centimeters cube is very important, because you may wonder where this number pop up from. Now let's go back to the question, right? And let me kind of make a zoom back in this so it'll be a little bit bigger. All right, so I want to point this out. This 48 is critical, yeah? So if you read this question, it said, use the equation to calculate the accurate mass of magnesium required to produce the final volume of hydrogen gas in the reaction at room temperature. First and foremost, how do we determine the final volume of hydrogen gas? Now your graph tells us this. Let's go back to the graph. All right, so I'm going back to the graph a bit. And this is a graph right here. I want to notice something with the graph right here. The two last temperatures, regardless of time, you cannot produce no more gas than 48. Okay, so if I even go back to your table, you notice in the table as well. So in the chart, you have C 48 and 48 right here, regardless of the time. So if you continue, there's no more gas can be formed, and simply because all of the acid was used up or neutralized. So beyond that point, since the magnesium was in excess, you cannot produce any more gas because all of the acid was used up in the reaction. In other words, all the acid was what? Neutralized. All right, so that's what we get our 48. All right, so from our 48 now, let's go back down a little bit here, because I know that's the critical point. You may wonder, where get this 48 from? But yes, the 48 came from the maximum amount of gas produced, which means that the reaction is completed and we're at the end of the reaction. So yeah. So what you need to do now, again, you have to convert your centimeters cube into your dm cube, right? And again, I make a note right here, see maximum gas produced in the chart or also in the graph. I could put chart or graph because it's also in the chart as well, right? All right, so I'm gonna put it right here, the chart or graph. Okay, great. All right. So what do you need to do from here now? Because the reason I convert the volume into dm cube is because the RTP volume was given as 24 dm cube, right? So I want to convert my centimeters cube into dm cube. All right, if you're going to use centimeters cube, then you have to use 2,400 centimeters cube as RTP. But nevertheless, I converted to dm cube. And so the mole here would be the volume divided by the conditions that we're using, and this RTP, which is 24. So you get 0.002 moles of hydrogen gas. Now, again, we want to find the mole of magnesium, right? So if you go to the reaction, and the reaction is very important here. If you go to the reaction, you realize that in terms of magnesium and hydrogen, okay, because again, you'd have to put a 2 right here to balance the equation, right? So to make the equation balance, a 2 must be placed right there. Okay, that's very important, right? All right, so let's jump down to it a little bit and do the calculation real fast, right? So in terms now of the equation right here, all right, let's go down back to it. RTP is 0.02. And now since the ratio in this equation is a 1-to-1 ratio, then the mole of magnesium is also 0.02. So again, go back to your equation. One more time. I want to show you this. It's a balanced equation. You have 2 atoms of hydrogen right here, 2 atoms of hydrogen. In fact, the equation is balanced, right? So you have 1 molecule of magnesium react with 1 molecule of sulfuric acid to produce 1 molecule of magnesium sulfate and 1 molecule of hydrogen gas. So again, the ratio is 1-to-1, regardless of the component you're using. Okay, that's why the mole of hydrogen gas produced is the same mole of magnesium used. All right, so I want to show you that. All right, so here we get it. So it is the same mole. However, now to find the mass of magnesium, it is a mole multiplied by the relative atomic mass, which is 24. So the mole multiplied by 24 gives you the mass of magnesium, okay, which is 0.48. All right, let's go to the next part of the question. It's the amount of magnesium remaining in the solution at the end of the reaction. Now, this is cool because here to calculate the mass of magnesium remaining, remember you use magnesium in excess, isn't it? All right, so at the end of the experiment, all the magnesium was not used up. But we calculated right above this question is the mass of magnesium right here, okay, which is this. So first and foremost, let us calculate the mass of magnesium that we actually add to the entire thing. If you should go back to go back to the equation right here. All right, let me just go back to it a little bit and it will show you our 35 right here in the question. All right, I'm too far up. All right, so I just want to show you the magnesium right here. Okay, that's the equation right there. All right, great. And so what I want to point out to you right here, I want to get this number now, right? Is that for us to get the value right here, again, based on the mole we calculate, then if we want to find the mass of magnesium added, it's going to be 0.035 multiplied by the relative atomic mass, which gives us 0.84 grams. That's the total that they add to the solution or to the reaction, the total magnesium. So the mass remaining now must be what they add from what was used up. Okay, so what they add to it from what you use up must be the difference. So that's what remaining. So what was used up, it is the amount that was neutralized or used to neutralize the acid. This mass that we calculate here, that I'm highlighting right now, that is the mass of magnesium that was used in the reaction. That was used in the reaction. Okay, so if that was used in the reaction, then from the total magnesium used, right, from the total magnesium used, which was 0.84 based on what we calculated right here, we're going to minus what was used from the total, and this is the remaining portion, which is 0.792 grams. Okay, so that's very important right there. Now, again, I just want to point out our 35, this value right here. Just want to point it out real quick because, again, I know this maybe you may say where this number pop up from. Just want to remind you of the question. Let me just quickly go back to the question. They gave us the moles of magnesium used, okay, or magnesium added. So let's go back to it real quick. I want to show you it. I don't want that to miss you at all. So in the question, okay, we almost, let me go a little bit faster. In the question right here. Right here in the question, it said that, yep, a student used 0.035 moles of magnesium. So that's a mole of magnesium added to the entire thing. So from that entire mole, we must have the entire mass. So if we multiply by 24, we get the entire mass used. But by calculation, we calculate that was used up was, I'm going back to that question. All right, so I don't want you to miss this at all. All right, so great, right here. Again, remember that they gave us this mole, yeah? They gave us this mole. So this mole multiplied by the RMM or the RMM of or AM of magnesium. This is the mass of magnesium added to the entire thing. Again, we've calculated the amount of magnesium actually used in the reaction, which is this value right here. And the difference between these two values, we get the remaining amount of magnesium. All right? All right, great. Now, part 4 right here, right? It said sulfuric acid, which is H2SO4, is a dibasic acid. It said how many moles of hydrogen ions, which is H plus ions, are present in 25 centimeters cube of sulfuric acid. Again, it's a 1 mark question. So again, what you need to think about here, we already can find our mass of sulfuric acid. This is based on the previous reaction. The mole, everything in the equation, a matter of fact, is a 1-to-1 ratio, right? So if this was a mole of hydrogen gas formed, then it's the same mole of sulfuric acid. And again, based on equations, a 1-to-1 ratio. Now, however, now what we're going to do now, again, we want to find here the amount of hydrogen ions in this. So hydrogen in H2SO4 is 2. So we're going to multiply the moles here, the entire mole, by 2 and then divide by 98. The reason why I do that is a kind of a percentage. So you can say 2 divided by 98 multiplied by 100, then multiply by the mole, you get the same answer, right? So it is a 2 because they are in HCl, sorry, in H2SO4, there are 2 atoms of hydrogen. The total mole, it is 0.02. So it's going to be 2 multiplied by 0.02 divided by 98. So it gives us a percentage ratio of the moles of the hydrogen ions within H2SO4. Okay, so that will be our moles there. All right, so let's go to now part C. In part C, is on your graph in A1, sketch the graph of results obtained if the experiment is repeated at a higher temperature. Now let's reason this out first. We'll go to that, right? If the experiment was done at a higher temperature, what will happen? Will you produce more gas? I don't think so. No, because once all of the acid was used up, you produce the same amount of gas in terms of volume. The difference with that heat will do to the reaction is to make the molecules move faster. You have a faster reaction, but the same amount of gas will be produced. So what will happen now is that you produce the same amount of gas, but in a short time. So let's go back to the graph. Let's do this real quick. I want to make this graph as possible, so you can see exactly what I'm going to do with this. So let us alone. Okay, great. So that's right there. All right. So what I'm going to do right here is to draw this now. You're going to be a little bit difficult, so I'll draw it twice. All right. So let me just put a red line in this one. All right. So follow me carefully. So this line again will produce the gas, but at a faster time. So it'll be above this line. So once your graph is above this line, you are good. But there's something specific I want to show you. All right, this is not totally smooth. All right, but I assure that you'll make your line smooth as possible. But what I'm going to do here is just to show you what I want on the top of this graph. All right, this graph's a little bit up. So let me just go back a little bit and ensure that I'm going to take this graph down a little bit from this line. All right, so I really want to show you this. Okay. I really want to show you this. All right, so yeah. All right, so yeah, I'm going to put it down a little bit. All right, what I want to have with this, now, okay, I'll put it back right here. So it'll be somewhere there. Cool, right there. And so I'm going to add on this next piece to it now. So you're going to see exactly what will happen here. Is that, again, as I mentioned to you, that the graph, the amount of gas will not be increased. So what's going to happen here? The 48 will be produced somewhere over here, right? In a shorter time. That's all going to happen. The same volume of gas will be produced, but in a shorter time period. Okay, I know you're going to make your graph a little bit better than mine. All right, so now let's just jump into now the other part of the question. All right, and see how quick we could finish with this. I know this paper 3 may take a little bit of time because of the length of responses and the explanation again. So we are somewhere, yep, we're right there. All right, so we have just finished that. Now for part 2, it said explain, let me give you some more zoom on this. It said explain in terms of collision theory the effect of increasing temperature on the rate of reaction. Again, what you need to know, if temperature increased, then the kinetic energy of a particle is increased. All right, and once the energy increased in the reactants or the particles, then there'll be an increase in the movement of these particles. The particles start to move faster, and because of the moving faster, you'll have more frequent collision or faster collision of particles. And once the particles are colliding much more and more frequently, then the rate of reaction will increase. Okay, and again, the rate of reaction will increase due to more frequent and faster collision of the particles. All right, that's what is taking place there. For part 3, it says state the effect of adding a catalyst. Adding a catalyst will have on the volume of hydrogen produced. Again, the volume will not change. The volume, the overall volume produced will not change. Simply because once all the acid is being used up in the reaction, no more gas can be produced. However, though, what will happen? The volume of gas will be produced at a faster rate. In other words, they have a greater reaction. So it takes less time to produce the same amount of gas, but it will not produce any more gas. The same volume will be produced. Now for part D, it says sulfuric acid, which is H2SO4, is manufactured by the contact process. It said one of the reactions in the contact process is shown. And here it said that you have 2 molecules of the sulfuric acid, of the sulfur dioxide, as a matter of fact, plus oxygen will give you sulfur trioxide, and is a reversible reaction. And now the part of the question is state and explain in terms of the Le Chatelier's principle, effect on the equilibrium concentration of sulfur trioxide if. So if you increase pressure, what will happen here? If you increase pressure, then the reaction will shift towards the product, which is shifting towards the right. And the reason for that is simply because the rate of reaction will also increase and produce more or fewer molecules. Again, the main reason why it shift towards the right, it will shift towards the one with the fewer molecules. It will shift towards one with fewer molecules. Let me explain to you what I mean. So let's go back to the graph. Notice here, on the left side, you have 2 molecules plus 1 molecule. That's 3 molecules in total, right? But on the right side, you have only 2 molecules of sulfur trioxide. So once pressure is increased, it will shift towards, we have a fewer molecules. So I tend to prefer those fewer molecules to kind of balance off the equation. Because remember, the idea is always require an equilibrium. Okay, always. And so shift towards the lower molecules. And so 2 molecules of sulfur trioxide is less than a molecule of oxygen and 2 molecules of sulfur dioxide. So you move from towards the right side, I should say, or towards the product side in this case. All right, now look at this other part of the question right here. Now, part 2. So sulfur trioxide is removed. If you remove sulfur trioxide, again, remember, in Le Chatelier's principle is always to achieve a balance. Let's think about the word balance or equilibrium. So if you remove sulfur trioxide, what will happen now, it will also shift towards the right. Why? Simple. Because it wants to replace what was missing to create that balance. You see? So if you cut off your fingers, for example, you want to grow back fingers quickly, eh? So you want to move to, if your fingers get cut off, you want to grab that hand and say, whoa, pain. And I want to grow back those fingers to make it be balanced again. So wherever it is missing, right? Wherever it's missing, that's where you want to go back to ensure that you come back to that equilibrium, right? If you have a water bottle and the time is hot and you drink the water out of the bottle, what are you going to do? Replace the water in the bottle, yeah? So you're going to move towards what was removed. So if you read this statement right here, it will shift towards the sulfur trioxide, which is the shifting towards the right. And simply because the reaction will produce more sulfur trioxide to make up for what was removed. Okay, great. All right, let's go to this part, part 2 now, which is this part. It said increasing the temperature causes the position of the equilibrium to shift to the left. So this is a different case scenario now. It shifts to the left if you increase temperature. Explain why the position of the equilibrium shift left. So let's talk about why shift left. It's simple. The reaction will shift left because reactants must use up the excess energy by producing, or the energy by the heat, yeah? Because again, what is using up the energy to break bonds and so on is the reactants. So if you put more heat inside of the reaction, then the reactants must use it up to make everything back to a normal. Okay, something must absorb that heat energy, and the reactants will absorb that heat energy. Okay, all right, great. Part F. It said give one industrial use of sulfuric acid, which is H2SO4, and you have a number of uses. This is only a few. Sulfuric acid can be used in so many different things. Yes, it can use in batteries. It can use in cell phones. You make explosives, make fertilizers. And you can also, and please do not try this at home, but you can use it to clean genuine jewelry, for example, gold and silver. And you know why? Because gold and silver, they cannot react with acid. And so any impurities that are in gold and silver will be washed away by the acid. But please do not try these things at home. Do not use acid at home. Please, disclaimer, do not do it. Okay, go to the professionals to clean your jewelry, please. Thank you very much. All right, let's go on to the next part of the question. Question number 6. All right, for question number 6, it says petroleum is a mixture of hydrocarbons. Study the diagram below and use your knowledge of organic chemistry to answer the following questions. All right, and so here now it's that state the method of separation shown in the diagram below, and this fractional distillation is a show on the diagram where the following groups of hydrocarbons are found. Group 1 hydrocarbons with 1 to 4 carbon atoms, and group B hydrocarbons with 15 to 25 carbon atoms, and that's 2 marks. But I'm going to show all these all these on this chart real quick. All right, let's see if I could put, I should try type them in. No, and I won't be able. Okay, let me just write them in real quick, yeah? All right, so here now, where the gasoline is, that will be about 5 to 10. So here will be 5 to 10. All right, where the gas is, which is at 20 degrees, that will be about 1 to 4 carbon there. All right, and again, as you notice, you go down in higher amount of temperature required, then therefore you know that the number of carbon also increase, right? So that's something you need to know again. So again, I think it said 1 to 4. So this is one of our mark. Yeah, I think it said 1 to 4. I'm going to go back to it to make sure that I'm doing the right thing in terms of which one I'm identifying as the answer. But I'm giving you all of them. And so kerosene will be about 10 to 16. Okay, so anywhere between 10 to 16 carbon. Diesel will be anywhere from about 17 carbons all the way to about 20 carbons, and this will be your answer here, say between 25. So anywhere right here will be your correct answer right here. Again, these are just estimated range. So again, anywhere from 15 to 25 will be here. Again, diesel oil is good for that. And then for fuel oil will be anywhere from about 20 to about 70. Okay. All right, but for the fact they said 15 to about 25, that means diesel oil is the most suitable answer for that. All right, and here we're gonna have, oh, I'm going too far, a little bit too far. All right, right here now, which is lubricating oils, generally start at about 20 as well, and will travel up to about 50 thereabout. All right, so great, that's how we have it there. All right, so let's go down to the next part question right here now. Right, and it said, okay, we added to complete this. We show the groups here, 1 to 4, which is the top one, which is 20 degrees. Okay, great, and 15 to 25, which will be about diesel oil. Okay, great. All right, so here now is a draw the structural formula for a saturated hydrocarbon. All right, that contains 4 carbon atoms. So once contains 4 carbon atoms, again, this is going to be butane. All right, it's a show the atoms and all of the bonds. And so if you notice here, what I want to point out, once you draw a carbon, right, there must be 4 lines, 4 total lines or 4 total single bonds around it. So you could have 2 double bonds, you can have a triple bond and a single bond, or 4 single bonds. So I draw the carbons. It is saturated, which means only single bonds. And so you notice only single bonds around the carbons. All right, so that will be our 1 mark answer right there. It's a draw name and isomer for your answer in part A3 above. All right, I want to point out something right here real quick. Again, you can make the hydrogen separated to be the structure. I just write a condensed structural formula just to save some time. But again, you could put the 3 carbons around, 3 carbons around, 3 carbons around, right? And so all you need to do is to change the arrangement of the atoms. And so once you change the arrangement, so this will be 2-methyl, which means the methyl group is on the second carbon, and is the 3 carbon on the longest chain, so it is propane. Okay, and again, it's ane because it's all single bond. All right, for part 5, it's a decane, which is C10AH22, is one of the hydrocarbons produced in 1A. Name the method by which decane can be broken down into shorter chain hydrocarbons that are more useful, and this process is called cracking. So once you break larger organic molecules or hydrocarbons into smaller ones, it is called cracking. And now for part 6, it says draw the structural formula for a saturated and unsaturated hydrocarbon formed when decane is broken down in the process 5 shown there. So there again, you're going to have 2 separate things. I just break them down in almost half, to be honest with you. But here I have, my hydrogen is all the way up to the top. Just make a note, the hydrogen is right here, right? And so what is happening here, just to make this note real quick, I went with 6 and 4. Okay, but remember, decane is 10 in total. So I went with 4 carbons and 5 carbons. So what I'm going to show you right here now, I'm gonna take off some stuff right here because one of them must be unsaturated. So I'm gonna show you something really quick. All right, to be unsaturated, what you're gonna do once you draw for example, you're going to remove, because unsaturated simply means that you have a double bond, right? So I'm going to make a double bond right here. All right, since that's not coming off, I'm going to just draw it on to show you exactly what I'm talking about. So I'm going to draw 1B double bond. So I'll make a double bond right here. And so I'm going to make a double bond right here. And once you make a double bond, you're going to take off the hydrogen atom. So you're going to take off this, and you're going to take off this. All right, so again, you could do it like that. That's the way to do it. You break it up into two saturated first, and then you could just take off the bonds that you don't need. Or wherever you're going to put the bond. You could put the bond at the end, you could put it in the middle, wherever you put it, that is also fine. All right, so great. So it's an easy way out of this. All right, so that will be your saturated. I want to erase this to make it even look better. Let's see if I could do that. I'm not sure why it's not allowing me. All right, but anyway, okay, awesome. Yeah, perfect. All right, great, good. So that's how you could do it. You could make two saturated, break them in two equal half, and then just take away the hydrogen, and you'll be totally correct. So perfectly fine. Awesome. All right, so again, you could put it at the end, or you could put it in the middle, or wherever you choose. All right, or if you know what to do it, just simply put a double bond and then go straight ahead. But unsaturated means you must have at least a double bond. Now for part 7, it says state a test and results that can be used to distinguish between saturated and unsaturated hydrocarbon. And so there are two tests that I'm going to show you right here, and it's the Bayer test or the permanganate test. And simply what you're going to do, you're going to if it is unsaturated, you will have a brown sludge formed, while no color change for saturated hydrocarbon. And simply because the saturated one will not react so easily, all right, because unsaturated hydrocarbons are more reactive than saturated ones, okay? Same way with the bromine water test, okay? So bromine water test, what they're going to use again, if you use a saturated hydrocarbon, there's no change simply because it is less reactive compared to the unsaturated, which is double bond one. And so while the unsaturated hydrocarbon will decolorize the bromine water, and there's a reason for that, because where the double bond is, it will react with bromine. So therefore you have a what they call an halogenation type of reaction taking place when bromine is reacted there. For permanganate is an oxidation reaction. So you're going to oxidize the unsaturated hydrocarbon. All right, so oxygen will be added to it. But in bromine, it is the halogenation, right, that is taking place right there, adding an halogen to the unsaturated hydrocarbon thing. All right, so now this is part 8. It's a write the word equation to show the reaction of propane and chlorine gas. And so propane here plus chlorine gas will give you chloropropane and hydrochloric acid. And here it asks us now to name the type of chemical reaction taking place. And this is halogenation or chlorination reaction. All right, adding an halogen. All group 7, they're halogen. So yes, they're called halogenation. All right, for this question now, we said an organic compound was found to be composed of 40% carbon and 7% hydrogen, and the remaining substance was oxygen. Calculate the empirical formula for this compound. And to calculate the empirical formula, what you're going to do, this is a long question, because this keep on going and going. All right, here now for carbon, so carbon is 40%, you're going to say 40 over 12 here. Assume that there's 100 grams of the substance. So when you say 40 divided by 12, we give you 3.33. Then you're going to say hydrogen is 7%, divided by 1, give you 7. And then you're going to say oxygen, which is 53%, divided by 16 to give you 3.3. What you do next is divide each of these numbers by the smallest number. Here the smallest number is 3.3. So therefore 3.33 divided by 3.3 pretty much give you 1. 7 divided by 3.3 pretty much give you 2. And this give you 1 as well. So the empirical formula is CH2O. Okay. So 1 carbon, 2 hydrogen, and 1 oxygen. So that's the empirical formula. All right, part 2, relative molecular mass of the compound is 60. So the relative molecular mass of the compound is 60. Give the molecular formula of the compound. This is a 1 mark question. And then the answer here now is the mass of the empirical formula. You need to know the mass of the empirical formula right here, which is going to be 12 plus 2 plus 16. Because remember, it is CH2O. So carbon is only 1. So let me see if I could go back a little bit up so you can see exactly what I'm doing. It's not going to be shown. So just remember that it's CH2. So therefore, here you have 1 carbon. So going to be 12 plus 2 hydrogen going to be 2 plus 1 oxygen going to be 16, a total of 30. So what you're going to do now to find the empirical formula is to divide the mass or the molecular mass over the mass of the empirical formula. You get that number. Then you're going to multiply that number by the empirical formula to get your molecular formula. And right there it is C2H4O2, and that is acetic acid. All right, great. All right, now part C1 is ethanol is an alcohol. Write the chemical equation for the formation of ethanol from glucose. And then once you're in bio class or remember biology class, you should know that glucose will undergo anaerobic respiration by yeast, right, to produce ethanol and carbon dioxide, plus some energy, of course, right? So we know that ethanol is C2H5OH, and you balance the equation by putting a 2 in front of the ethanol, okay? And so you will be good right there. A matter of fact, you need to put 2 also in front of the carbon dioxide as well, all right? And so let's put that 2 right there. All right, so right here you have 4 carbon, and then you have 2 more carbon, make 6. All right, and then 12 H's, and then 5. All right, and 2 is 12 as well. All right, so that equation is balanced. All right, great. Now, it's the ethanol can form ethanoic acid. What type of reaction is this? And to form ethanoic acid from, or you may want to say ethanoic acid, from ethanol, then you're going to oxidize it. You're going to add some oxygen to it. And once that oxygen to it, it becomes acidic. Okay? And even this process may take place when you're making alcohol as well. If you expose the alcohol to oxygen, then bacteria will enter it and start to respire and then oxidize the alcohol and forming vinegar. Okay? All right, so question number 7. This is the last question now, and we're out of here. Now, this question here now, it said that the equation shows the formation of iron chloride, right? So here, we want to point out the equation. So we have the equation right here, and it's a balance as well. It's a state which substance is oxidized and which substance is reduced. Give a reason in terms of electrons for each answer. And let me point this out real quick. When you say oxidized, the substance that's being oxidized, that means therefore it reduces another substance, right? So an oxidation in terms of electrons is when you lose electrons, right? All right, and when you reduce is when you gain electrons, just to make a note of that. All right, and so here now, the answer, it is the iron chloride. This is supposed to be 3. Okay, no, that is 2. That is correct. That is Fe2Cl, right? So Fe2Cl, Cl2 is oxidized, and because it lost electrons, chlorine is being reduced because it's an oxidizing agent. I'm gonna tell you why chlorine is a good oxidizing agent, right? So it is being reduced, all right, and because it gains electrons. Because remember now, chlorine is an halogen. It belongs to group 7. Group 7 elements, they react really well by taking on electrons. So you can, in other words, you can say that group 7 elements tend to be more electronegative than most other non-metals, right? All right. Of course, you know there are some variation based on the group and groups, based on the periods, as a matter of fact. All right. And so definitely we know that chlorine is a good oxidizing agent because it tends to gain electrons to itself, right? Part B. It said iron is extracted from its ore, which is hematite. All right, the ore is mixed with limestone and coke to extract the metal in the blast furnace. The equation for the is shown, and here it said iron 3 oxide plus carbon monoxide to give iron and carbon dioxide. It's a name the reducing agent in the reaction, and the reducing agent right here is carbon monoxide. And again, why it is a reducing agent? because it itself is being oxidized. And so carbon monoxide will gain oxygen, right? Will gain oxygen to become carbon dioxide. I think I never answered above. Oh, yeah. Okay, I did answer it. When I just remember about lost electron and gaining electrons. All right, so once oxidized, it means that lost electrons. Once reduced, it means that it gain electrons. I thought I never answered that. Great. All right, so here to write a balanced chemical equation for the reaction again. It will be iron trioxide plus carbon monoxide, give it iron, and then that will be the balanced equation. It's a calculate the mass of iron produced in kilograms from 5 kilograms of iron 3 oxide. And so the first thing you want to do again, if you want to get this in kilograms, all right, the first thing you want to find is the molar mass of iron, all right, of iron 3 oxide. So the molar mass here, again, it is iron, which is 56 multiplied by 2 because there are 2 atoms of iron. Oxygen, which will be 16 times 3 because there are 3 atoms of oxygen, and a total here of 160. Now, the 160 grams that you get, you can convert that into kilograms by dividing by 1,000, you get 0.16 kg. All right, so once you find the mass in kilograms now, that is the molar mass in kilograms, you can go ahead and find the moles. How can we find the moles now? Remember the mass given, it is in kilograms, so 5 kg divided by the molar mass or the relative molar mass in kg as well, you get 31.25 moles. There's another way to do this. You could calculate using mass, using grams first, and you have to convert by the final answer in the kilograms, but that's like double work, so you don't need to go through all of that. All right, now once you find the moles, all right, again, you need to look at the ratio in equation. So if you go back to the equation, you notice that there's a 1:2 ratio in your equation here. So this is a mole of the iron 3 oxide, which is 31.25. But we're going to find the mole of iron now. And so let's go back to the equation. I want to show you real quick. So see, in the equation right here, this is 1 molecule of iron 3 oxide to 2 molecules of iron. So that is why we have to multiply that mole by what? 2. Okay, so since we get this mole, you have to multiply it by 2 to get the mole of iron itself. And so here now to find the mass of iron, it is the mole of iron multiplied by the relative atomic mass. And the relative atomic mass I calculated in kilograms because the relative atomic mass for iron is 56 grams, but in kilograms, you divide by 1,000. So you divide the 56 by 1,000, multiply by the moles that you have calculated, and you get your mass in kilograms, 3.5 kg. All right, great. And then now, here's the 2 unknown solutions, X and Y, are tested. The test and results are shown. So solution X is added to potassium iodide solution. Iodide is produced. So this is a very unique thing that is happening here. You produce iodine, but you produce iodide, and then it said red cloth is bleach. Let me put everything on one place, one page, so at least you could see this. So bleach, red cloth. Motherfucker, if you bleach any cloth, you know what gas is there or what is in that solution. It's chlorine, isn't it? Right? Because remember, chlorine is a bleach substance. All right, it will bleach the clothes or the cloth. And so we can identify the solution. This X will contain bleach, is a solution of chlorine. And then for solution Y, it's when added to excess copper-2 sulfate, a deep blue solution is formed. And so this could be, well, I won't say it's 2 things, but if they have stated that anhydrous copper sulfate, they know that this will be water. But there's something else happening here. It said when warmed with sodium hydroxide, right, it produces alkaline gas that turns moist litmus paper blue. And so the alkaline gas that is formed right here must be ammonia. All right, so here we can state that X is the chlorine. Okay, so X will be chlorine, our solution of chlorine. Okay, so it'll be a chlorine solution right here. And Y here now will be ammonia. All right, because ammonia will be produced, all right, and will turn the red litmus into blue. All right. All right, so that would be your solution. A solution of chlorine, a solution of ammonia. All right, so great. Now, in the next part of the question right here now, I have to go back to the chart. So I'm going to go back to the chart real quick. All right. And so I'm coming back to this part of the question right here. All right. Let me just quickly do this. All right. Great. All right. And so this is where I want to get to now. This is the last part of the question, very last part of the question. It said the following diagram, the following diagram shows information on 10 substances, A to J. This is a long one. It's a solution. A turns blue litmus red. It reacts with silver nitrate and dilute nitric acid to produce a white precipitate. All right, so let's see what's going on right here. So we're going to identify these things. All right, let's go start from the middle. It said this is acid A. So this is an acid. That's a big clue. It says solution A turns blue litmus red, naturally because it's an acid. It reacts with silver nitrate to produce a white precipitate that turns gray in sunlight. All right, so here now that's an next clue. So by means of this, that it reacts with nitrates, with silver nitrate, they know it's going to be a chloride, right? All right, so you can know that this acid must be hydrogen chloride or hydrochloric acid. So let's call this HCl. All right, so this is HCl. By nature of what is being produced right here, it reacts with silver nitrate to produce a white precipitate that turns gray in sunlight. All right, so know that must be a chloride there already. All right, let's see what we can pick up from here. Let's go to B. It's a solution B. Now, if hydrochloric acid react with an alkaline, it produces salt and water, right? So, but now the salt itself, we know that there's a chloride in that salt, right? But we have figured out now what react with the chloride. So we don't know what alkali this is. So we need to figure out what it is. But this simple chloride is a positive ion in B produces brick red flame, brick red flame in the flame test. And calcium is what is produced that brick red flame in the flame test. So we know that this is reacting with the chlorine from the acid. So it must be calcium chloride solution. So here I'm going to put calcium chloride right here, solution right here. All right, so this is calcium chloride. Okay, and we know it's chloride because the hydrochloric acid here. All right, so it produces salt and water. So it is a calcium chloride solution. It's the aqueous form. All right, so let's see if we could figure this one out. G, and then we can work ourselves up. So this one react with metal carbonate. So if it react with the metal carbonate, you're going to get salt, carbon dioxide, and water. So by virtue of this, liquid I has to be water, because that's water. The gas must be carbon dioxide, so this is going to be water. So I has to be water. H, gas H must be carbon dioxide. So I'm put carbon dioxide right here. Okay, H must be carbon dioxide, because remember, acid plus carbonate give us salt, water, and carbon dioxide. So substance G has to be the salt, because this here is a liquid, you see. All right, so this is carbon dioxide. All right, so now substance G now, again, we say it must be a salt. But which salt is it? Let's figure out. The positive ions produce golden yellow flame in the flame test. Gas H also turns lime water milky. So we already figure out that gas H is carbon dioxide. This is another clue that it turns lime water milky. Carbon dioxide does that. So here we can say that sodium is what will produce the yellow flame, the golden yellow flame in the flame test. So therefore, this here must be sodium chloride that is formed right here. All right, so sodium chloride. So the carbonate will be sodium carbonate. The carbonate is used as sodium carbonate. So this must be sodium chloride. I'm going to write this NaCl just to make it time short instead of writing out the whole name. But again, you want to write out the names, right? That is sodium chloride that is formed right there. But I want to do this real short because of the space as well. J, let's see if we could figure out J. All right, they said the fumes of solution A reacts with ammonia gas. Okay, that's a cool one. It's a common experiment right here. So if hydrogen chloride react with ammonium gas, it forms a white solid, right? And so the white solid will form right there is ammonium chloride. So J has to be ammonium chloride. And if you remember that little experiment that they put the hydrogen chloride in one end of the gas chamber or the gas tube, and then you put the ammonium hydroxide in one end, and then you see the fumes going out, and then a white ring form in the middle. That's a very cool experiment. So if you remember that one, then you know you're good. So this is ammonium chloride. All right, great. All right, let's jump to the next part up here now. We're almost there. We're almost finished. All right, so this one now that reacts with metal C. So react with metal C now. So that's a metal reacting, which is a very good thing. So hydrochloric acid react with metal. You know that the gas form must be hydrogen gas. Because remember, acid plus a metal give you a salt and hydrogen gas. So even though they give us a clue right here that they give us a squeak popping sound, know that this is hydrogen gas. So this is hydrogen gas right here, right? So hydrogen will make a popping sound in the presence of light or fire. All right, so salt solution now. When you figure out what salt solution this is, right? So the salt solution, let's see if we give, okay, right. There's a clue right here. It's the metal C, when burned in air, produce a dazzling white light. So to burn this metal in air, you get this dazzling white light. So what metal does that is magnesium, okay? But we want to figure out what the solution did though. Because if it's magnesium reacting with hydrochloric acid, right? Because remember, hydrochloric acid is the center of the thing right here, right? So that's hydrochloric acid. So if hydrochloric acid react with magnesium, then it must get magnesium chloride, okay? So magnesium chloride is D, magnesium chloride. Yeah? All right. And then for F, which is the last thing and we're out of here, it's a solution F now, right? It's a positive ions produce a blue-green flame in a test, but this react with a metal oxide. So now we have to figure out what the metal oxide is now, right? But the fact of the matter is, here we're going to get two things, as a matter of fact. The acid plus metal oxide will give you the salt solution and also water. But the fact that they say this the positive ion produces blue-green flame in the flame test, you know that is copper. So this metal oxide is copper oxide, right? So copper oxide react with hydrochloric acid will give a copper chloride, right? And water. So this here is copper chloride. All right. So this is copper chloride. This was a long one. Yeah, we're finished. We are out of here. I really hope that you pass your exam. Do well, please. Just take care of yourself, all right? All right, enjoy and be good.